Welcome to this specialized course. The goal of this course is to equip you with the strategic clarity needed to deploy next generation AI. Historically, we have grouped AI under one umbrella, but the era of generic AI, the AI of creation, is evolving into the AI era of agentic AI, the AI of action. The core distinction is this: generative AI systems such as ChatGPT and Midjourney are focused on content synthesis. They create a novel output and then halt. Agentic AI systems built on frameworks like LangChain and Creo AI are designed for autonomous goal achievement. They plan, they execute, and they adapt. This course answers the most critical question in AI strategy: when does a task require a creator? When does it demand an autonomous doer? Regardless of your current role, whether you are an AI or machine learning enthusiast seeking architectural depth, a software engineer focused on implementation, or a business leader determining organizational efficiency, this course is designed to transition you from being a user of AI to an architect of automated systems. By mastering the fundamental differences and critical applications of generic versus agentic AI, you will gain the expertise to choose the right tool for the job, deploy complex solutions, and demonstrate true expertise in the future of automation. This course is divided into five modules. So, in the module 1, that is related to the foundational concept of AI, so there are four lectures. In the lecture 1, it is related to Introduction to Artificial Intelligence. Lecture 2 is Understanding Generative AI, and lecture 3 is Understanding Agentic AI. Lecture 4 is Key Differences at a Glance. Module 2 is Deep Dive into Generative AI. Lecture 1 is How Generative AI Works. Lecture 2, Core Use Cases of Gen AI. Then Lecture 3 is Prompt Engineering for Gen AI. Lecture 4 is Hands-on Project Building a Content Generator. Related to deep dive into agentic AI. So lecture 1 will be related to the architecture of an AI agent. Lecture 2 will be related to agent design patterns. Now we will come to know about the frameworks for agentic AI in lecture 3, and in lecture 4 it will be related to hands-on project building a simple research agent, practical applications and real world scenarios. So we'll cover first the lecture 1. It will relate to when to use Gen AI versus agentic AI. In lecture 2, blending the two Gen AI within an agent. Lecture 3 will be more with the case studies, and finally that will be covering the future of AI and human agent collaboration. In module 5, the final module, that will be covering advanced topics and conclusions. Like in lecture 1, it will be related to ethics and governance in AI. Lecture 2 will be deployment and production. So there will be a final project like a multi-agent system that will be covered in lecture 3, and finally that will have a post conclusion and next steps. So some additional resources like all the code files and key research papers, glossary items, question and answer section that we will also link with the course. What is artificial intelligence? So it's a science of making machines that can think, reason, and learn like humans. Coined by John McCarthy in 1956 at the Dartmouth workshop, the official birth of the field, AI aims to automate intelligent behavior. So this slide introduces the Turing test, a fundamental concept in the history of AI. It correctly identifies the test as a method proposed by Alan Turing to determine if a machine can demonstrate intelligent behavior that is indistinguishable from that of a human. The key idea is that if a human interrogator can't tell whether they are conversing with a machine or another human, the machine can be considered intelligent. This concept has been a cornerstone for decades, helping to frame the goal of artificial intelligence as in mimicking human thought and communication. So it's a foundational concept that sets the stage for understanding the more advanced forms of AI we see today, including Gen AI, which is modern and highly successful attempt at passing a more specialized version of this test in creative and conversational tasks. So in the previous section, we talked about the history of artificial intelligence. Now let's bring it all into the present and ask the most important question: why is AI so important right now? So the first point on the slide highlights that AI is no longer a futuristic concept. It's a technology that is actively transforming industries and our daily lives. Think about the cars that can park themselves, the navigation apps that give you real-time traffic updates, or the chatbots you use to get customer support. All of these are powered by AI. Next, we see that its rapid advancement is a result of two major technological changes: the growth of big data and powerful computing. We now have access to enormous amounts of information that can be used to train AI models, and the processor to handle that data are more powerful than ever before. This combination has allowed us to accelerate what AI can do at an incredible pace. Finally, at its core, AI is important because it can solve complex problems more efficiently than humans. This is not about replacing people, but about augmenting our abilities. AI can analyze millions of data points, identify patterns, and make predictions in seconds, tasks that would take a human a lifetime to complete. It allows us to tackle challenges that were previously impossible to solve. So, as you can see, AI's importance today comes from its tangible impact on our world, the technological advancements that have powered its growth, and its unique ability to solve problems on a scale that was unimaginable just a few years ago. This slide traces the evolution of AI across three major eras. We begin in the 1950s with Alan Turing's foundational work and the creation of Eliza, one of the earliest chatbots. The 1980s saw a slowdown known as the AI winter, but expert systems like XCon sparked a revival. Then, from the 1990s to 2010, machine learning took center stage, highlighted by IBM's Deep Blue defeating Gary Kasparov, and the rise of deep learning powered by big data and GPUs. Each phase laid the groundwork for today's intelligent systems. Thus, it illustrates the evolution of AI from rule based systems to deep learning. Early artificial intelligence was built on rigid, hand coded rules effective for simple tasks but easily broken by unexpected inputs. Then came machine learning, which allowed systems to learn patterns from data, both labeled and unlabeled. Today, we are in the deep learning era where powerful neural networks drive complex tasks like image recognition, natural language processing, and generative AI. This progression marks a shift from static logic to dynamic intelligence. Generative AI marks a major shift from traditional AI. While earlier systems focused on prediction and classification, Gen AI unlocks creativity by generating entirely new context, whether it's text, images, or code. Its strength lies in novelty, diversity, and contextual understanding, allowing it to produce outputs that are both original and relevant. The recent boom in Gen AI is fueled by access to massive datasets, making this technology more powerful and accessible than ever before. This slide provides a foundational understanding of large language models, which are at the heart of generative AI. LLMs are sophisticated neural networks trained on vast amounts of textual data, ranging from books and articles to web pages. Their primary function is to predict the next word in sequence, but this seemingly simple task enables them to generate coherent, contextually rich, and human text across a wide variety of domains. The site highlights how LLMs works and what makes them powerful. First, they possess contextual understanding, meaning they can interpret the intent and nuances behind a user's prompt. This allows them to respond in ways that are not only grammatically correct but also contextually appropriate. Second, they excel at text generation, which includes tasks like writing emails, composing articles,
summarizing lengthy documents, and even translating languages. Some of the best, most well known examples of LLMs include GPT-3, GPT-4, and GPT-5 by OpenAI, which power ChatGPT. Bard, now Gemini by Google, and Llama by Meta. These models have revolutionized how we interact with machines, making it possible to have natural conversations, automate content creation, and enhance productivity across industries. In essence, LLMs are not just tools for generating text, they are engines of understanding and creativity. Their ability to learn from massive data sets and produce meaningful output is what makes them central to the AI revolution. So, continuing from the previous slide on large language models, this slide showcases how those powerful models are being applied across industries to drive real world impact. In content creation, LLMs are used to generate marketing copy, scripts, and social media posts, helping brands maintain consistency and creativity at scale. Moving to customer service, these models power intelligent chatbots and virtual assistants that can handle queries, resolve issues, and provide personalized support 24/7. In the education sector, Gen AI enables personalized learning experiences by creating tailored study materials and offering tutoring support based on individual needs. This helps educators scale their efforts and reach diverse learners more effectively. Finally, in software development, LLMs assist developers by auto-completing code, identifying bugs, and generating documentation. This not only speeds up development cycles but also improves code quality and team productivity. Together, these examples illustrates how Gen AI is not just a technological breakthrough, it's a versatile tool reshaping workflows and unlocking new possibilities across domains. This slide shifts focus to another powerful branch of generative AI, that is diffusion models, which go beyond text to generate visual content. These models work by starting with random noise and gradually refining it into a meaningful image guided by a text prompt. It's like turning static on a TV into a detailed picture. During training, they learn how to add noise to images, and during generation, they reverse that process to create stunning visuals. Popular examples include Midjourney, Stable Diffusion, and DALL-E, which are known for producing high-quality, detailed, and artistic outputs. These models are especially effective in capturing textures, styles, and fine details, making them ideal for creative tasks like art design and visual storytelling. Building on diffusion models, this slide highlights their diverse applications, from generating photorealistic images and videos to creating 3D content and transferring artistic styles. They are even being explored in medical imaging, showing how Gen AI is expanding far beyond text into powerful visual domains. Introduces the concept of agentic AI, highlighting its evolution beyond simple prompt response interactions. Unlike basic LLMs such as ChatGPT, which are reactive, stateless, and passive, agentic AI functions as an autonomous, goal oriented system. It does not just answer questions, it perceives its environment, makes decisions, and executes multi step, self directed tasks. The key shift emphasized here is from single turn prompts to multi turn process driven interactions where the AI works more like a digital worker. While traditional LLMs provide immediate responses, Agentic AI demonstrates proactivity, initiating actions that align with a long term objective. It is stateful, meaning it can maintain memory and context across interactions, and active, capable of leveraging external tools like code, APIs, and the web to achieve outcomes. In essence, Agentic AI transforms AI from a conversational assistant into a strategic collaborator, opening pathways for more complex, dynamic, and autonomous applications across industries. The core principles of agentic AI focusing on goals and planning, which form the foundation of its intelligence. The first principle, goal oriented behavior, emphasizes that an agent operates with a clear, high level mission rather than responding to isolated queries.
Instead of merely answering, "Tell me about sustainable packaging," it undertakes the broader task of researching market trends in sustainability. This goal driven approach allows the agent to persist, refine, and retry until the objective is achieved, making it resilient and adaptive. The second principle, planning and decomposition, explains how agents handle complex objectives by breaking them down into smaller, manageable subtasks. Through step by step logic, the agent creates a structured plan of action, ensuring systematic progress. Additionally, the element of reflection allows the agent to evaluate completed tasks, adapt strategies, and dynamically update its plan. Together, these principles highlights how agentic AI mirrors human-like problem solving with persistence, structure, and adaptability. Of memories in LLM agents. Short-term memory is the immediate context window of the LLM, which is volatile. Long-term memory is achieved through retrieval augmented generation (RAG), using vector databases to store past experiences and learned behaviors. A more sophisticated concept is reflective memory, which periodically summarizes complex past events into concise, actionable long-term insights to improve future decision making. The second core principle is tool use or extensibility. This refers to an agent's ability to utilize external APIs and functions, allowing them to interact with the real world beyond simple text generation. Examples including web browsing and running code for calculations or data manipulations. These principles are key to create more capable, context aware, and effective AI agents. This slide titled Core Distinction Creation versus Action clearly differentiates between generative AI and agentic AI. Generative AI is defined as a creation engine. Its goal is to generate novel content like text, codes, or images based on a single prompt. Its mode is reactive and single step. It takes an input, processes it, and produces an output. Primary focus is output quality and creativity. In contrast, Agentic AI is an execution engine or a digital worker. Its goal is to achieve a complex multi step objective within an environment. Its mode is proactive and iterative. It acts, reflects on the result, and repeats this process until the goal is met. An effective analogy illustrates this difference. Gen AI is the designer, artist, or creative content creator, while agentic AI is the project manager or engineer system that executes a plan. This distinction highlights the shift from mere content generation to complex, goal directed action.
Now, what is the core distinction between generative AI and agentic AI, which is central to how these technologies are applied? Generative AI or Gen AI functions primarily as a creation engine. Its goal is to produce novel content, whether it's text, code, images, or audio, based on a single prompt. It operates in a reactive and single step mode, meaning it takes an input, processes it once, and delivers an output. The focus here is on creativity and quality of the generated content, making Gen AI ideal for tasks like writing, designing, or composing. In contrast, Agentic AI is an execution engine, a digital worker designed to achieve complex multi step objectives. It operates proactively and iteratively, meaning it does not just respond, it acts, reflects, and adapts until the goal is met. This makes it suitable for tasks that require planning, decision making, and interaction with external tools or environments.
Distinction, creation versus action. This slide titled Real World Examples illustrates the practical difference between Gen AI and agentic AI. Generative versus agentic AI example. Generative AI, the creator focuses on single step creation of content. These applications include generating marketing copy, that means variations of headlines, art and design, creating an image from text, and writing code snippets, a Python function. Its strength lies in pure content output based on a prompt. Conversely, agentic AI, the executor is designed to achieve a complex multi step goal, such as find the top three competitors for company X and summarize their Q3 performance. Achieving this goal requires a structured sequence of actions, agent steps, that means searching, using tools like reading reports, synthesizing the summary, and iterating. Thus, agentic AI is ideal for
task requires planning, interaction with external systems, and iteration to succeed.
Module 2, where we will take a deeper dive into generative AI, building on the foundational concepts you have already covered. So, the core of generative AI is revolutionary because it moves beyond classification to actively generate new content like text, code, or images that is original yet statistically consistent with the data it was trained on. This is the key shift. AI is moving from dissemination or passively identifying what already exists to active generation, creating novel data. The underlying operational principle for LLMs is fundamentally predicting the next word or token. The model does not understand content like a human. Instead, it uses its immense training to calculate the probability of what element should logically comes next in a sequence. As shown in the example, Matt is chosen because it is statistically most probable token. This simply scaled up probability engine is what allow LLMs to produce coherent, creative, and complex outputs. This slide, titled The Underlying Architecture, the Transformer, explains the core innovation that powered the generative AI revolution, essential backbone of modern Gen AI. Before it, previous neural network architectures like recurrent neural networks struggled with the problem before processing very long sequences of text efficiently, often forgetting information from the start of a sentence as they reach the end. The solution was a radical shift from sequential processing to parallel processing. This was achieved through the attention mechanism, the architecture's crucial idea. When the model generates a new word, it does not read the preceding words one by one. Instead, it instantly calculates and weighs the importance of every other word in the input simultaneously. This specific feature, called self attention, allows the model to instantly grasp the relationship and context between words, even if they are far apart in a sentence. This parallel approach is what provides the necessary scalability for a model to train on massive data sets, trillions of tokens, and scale up to billions of parameters, leading to today's powerful LLMs. Training process breaks down the typical two-phase methodology used to create modern powerful large language models. Phase 1 is the pre-training, the foundation. This phase builds the model's core intelligence. It uses a massive diverse datasets like the entire digitized internet with the goal to learn fundamental language structure, grammar, context, and general world knowledge. The mechanism is unsupervised learning. The model is simply trained to predict a masked out word or the next word in a sequence. The output is the foundational LLM, which is brilliant but raw and unaligned. Phase 2 is the fine tuning and alignment, making it more useful. This phase refines the foundational model with the goal of making it helpful, safe, and good at following instructions. This requires supervised learning and human intervention utilizing two main techniques. First is the instruction tuning, training the model on thousands of high quality examples of conversational prompts and ideal responses. And in the second step, reinforcement learning from human feedback, that is, the humans rank different model outputs for the same prompt, and this feedback is used to further optimize and align the model's behavior to human values and expectation. So this two-step process transforms a basic production engine into a highly capable and functional AI assistant. So the harnessing the power of the training process we just reviewed. This slide illustrates the two most common and impactful applications of Gen AI: content creation and summarization. In content creation, the primary goal here is to massively accelerate the production of high quality targeted text. The underlying mechanism is the Gen AI model's ability to instantly understand and replicate a specific tone, audience, and document structure. The key benefit is a dramatic reduction in time to draft from hours down to minutes, shift human effort away from initial writing and towards crucial editing and strategic refinement. Second is the summarization, the reader. In contrast to creation,
Summarization's goal is to efficiently extract the most critical information from vast amounts of text. This is achieved using the advanced alignment techniques from the training process, specifically instruction tuning and reinforcement learning from human feedback. These techniques ensure the model acts as a highly effective reader capable of filtering noise and isolating core facts to provide concise, accurate responses.
Now, shifting our focus from natural language text, this slide highlights another crucial area where generative AI excels: code generation and explanation, positioning Gen AI as an indispensable tool in the software development lifecycle. So, Gen AI in software development, first is code generation, the junior developer. The goal here is to help developers write, complete, and debug code across dozens of programming languages. The mechanism underpinning this capability is the training of models on billions of lines of public code. This massive exposure allows the AI to deeply understand not only syntax but also best practices and the logical structure of software. Its practical applications range from code completion to drafting complex multifunction blocks, significantly speeding up development time. Next is the code explanation and review bonus use case. Gen AI also serves a vital function in reviewing and maintaining existing systems. This bonus use case involves the AI analyzing code written by humans or other systems to explain its purpose, helping new team members quickly onboard. Furthermore, it can proactively identify potential security flaws or suggest performance improvements, acting as an always on expert reviewer to enhance code quality and stability. So, bridging the gap between pure data and human understanding, this slide illustrates Gen AI's critical role in data analysis and synthesis, transforming raw figures into actionable insights. So, GenAI's first key function is data analysis and interpretation, converting complex raw structured data like tablets, spreadsheets, or JSON into natural language insights. The mechanism involves the model processing the data directly or by intelligently generating code to perform calculations. The applications are vast, including automatically generating executive summaries from financial statements for reporting or helping researchers interpret scientific data and formulate hypotheses. The second core capability is the synthesis power, combining disparate pieces of information such as marketing data, customer reviews, and internal sales figures to create a unified, actionable report that human analysts can immediately use for decision making.
Moving from model capability to practical usage, this slide introduces the critical discipline of prompt engineering and breaks down the structure required to unlock Gen AI's full potential. Anatomy of an effective prompt. Prompt engineering is defined as the discipline of designing and refining inputs prompts to guide large language models toward generating the desired accurate and high quality outputs. Effective prompts are not just questions, they are structured directives built around. There are four core components of effective prompt. First is the role, defines the AI's persona, instructing the model to act as a specific expert, example, a financial analyst, an engineer, a chef. So these can be the roles. So second is the instruction. Instruction is basically defining the task, specifying the main action the model must perform. And third one is the tone or the format, like defines the style and structure dictating how the output should look and sound, example like professional report, a casual email. And fourth one is the output constraint, like you need to define the limit, setting boundaries for length, date, or explicit exclusions, like keeping the summary under 150 words. So, combining these components moves prompting from guesswork to a precise science. Building upon the anatomy of a prompt, this slide introduces the foundational strategies used to structure the prompt itself, that is, distinguishing between zero shot and few shot prompting. In zero shot prompting technique, this is the simplest technique involving giving the model a task with no examples. It relies purely on the model's pre trained knowledge and is best suited for straightforward tasks, such as asking for a definition like define quantum computing or general information. The model uses its massive foundation training to generate the response directly. In few shot prompting technique, it harnesses the power of examples, like it involves providing 1 to 5 examples of the input output format before presenting the final query. In the example, like mapping a color name to its hex code, the model quickly learns the desired patterns and structure. This technique significantly boosts performance and accuracy for complex patterned or subjective tasks, as it effectively programs the model's short term context window. In chain of thought prompting, which unlocks complex reasoning capabilities in LLMs, the core concept is to explicitly ask the model to show its step by step reasoning before providing the final answer. This technique effectively mimics human internal thought process. The primary use case involves challenging tasks like complex mathematical problems, logical deductions, or multi step reasoning. The key instruction is a simple phrase such as think step by step, or first outline the logic, then provides the conclusion. The resulting benefit is profound. It forces the model to slow down its generation process, allowing it to allocate more computational steps to internal logic, dramatically improving the accuracy and robustness of answers on tasks that require critical thinking. As we refine our prompting skills, this final slide provides essential guidance on navigating the challenges of interacting with LLMs, highlighting common pitfalls and best practices for reliable output. There are three key pitfalls to avoid when designing prompts. First is vagueness, using generic terms like good or do better, which provides the model no clear direction. Second is ambiguity, asking a question with multiple valid interpretations which lead to unpredictable results. Third is over constraint, adding too many conflicting instructions in one single prompt which confuses the model. To counter these, effective best practices include being specific about the desired quality and depth, providing context and defining niche terms, breaking complex tasks into smaller sequential steps, mirroring chain of thought, telling the model what to do rather than what not to do. Example, use a casual tone, not don't sound formal. Now that we have covered the theoretical foundation of Gen AI, this slide transitions us to practical application, outlining a project to build a simple content generator and necessary tools. The objective is to create a lightweight web application that takes a user prompt and uses an AI API to generate and display custom text or an image. This project is designed to clearly demonstrate the complete end-to-end workflow: user input, then API call, then output display. To achieve these three required tools and setup components are needed. First one is the AI API, the core LLM or image generator. This requires an API key for authentication. Second is the front end, a simple user interface built with basic HTML structure and JavaScript to collect the prompt. Third is the backend logic, JavaScript's function to handle the crucial steps of making the API request, error handling, and processing the JSON response. The project will apply key concepts like prompt engineering and JSON data handling. This moves us from theory to hands on implementation. To realize the content generator project, this slide visualizes the four sequential steps for the complete end to end workflow of interacting with an AI API. First is the prepare prompt client side. Capture user input and structure it into clear, effective instructions. Second is the construct request. Build the JSON post payload, including the API URL. the user prompt, and optional system instructions. Third is the API call. Execute the fetch command, sending the configured request to the server. Critically, a loading UI must be implemented immediately. Fourth is the process response, server to client. Upon success, extract the desired text or image data. On failure, handle errors gracefully and display a friendly message to the user. Concluding the practical roadmap, this slide covers display, iteration, and next steps, guiding the finalization and future expansion of the AI project. For displaying the output, text is rendered directly while an generated image is set as the image SRC. A crucial final step is post-process to mitigate hallucination in text or unwanted element in images. The primary challenges are latency and cost management. Mitigation involves showing a spinning loader and using smaller, faster models like Gemini 2.5 Flash for simple queries. Next steps focus on expansion, such as implementing a history tuner and adding controls for advanced prompt engineering parameters like temperature for creativity and max tokens for length. In Module 3, we will deep dive into Agentic AI. Transitioning from simple creation to goal oriented action, this slide introduces the essential architecture of an AI agent, which is designed for autonomous and iterative execution. The core concept is beyond generation. Agentic AI moves beyond simple generative AI by taking a sequence of actions to achieve a complex goal. An agent is composed of three key components: LLM, this serves as the brain that reasoning decision making, the central decision maker that interpret the initial task. Tools, these are the hands, execution or action, which are external capabilities like search, code execution, or APIs used to interact with the real world. Third is the planning loop. This is the strategy, iterative improvement, the mechanism that breaks down complex tasks, executes steps using the tools, evaluates the results, and course corrects. The combined goal is to convert a single user prompt into multi-step action plan that reliably leads to a complex, successful outcome. Leveraging the analogy of the agent's brain, this slide details the critical role of the LLM, the agent's brain and reasoner, focusing on its central function of deliberation. The large language model is the core engine for all high level thinking and decision making within the agent architecture. This deliberation process includes four key cognitive steps. First is the interpretation. The LLM first understands the user's high level goal and translates it into a concrete, measurable objective. Second is reasoning. It evaluates this objective against its memory and available tools to formulate an initial strategic plan. Third is the tool selection. Based on the current step, the LLM determines precisely which tool is needed, be it a search engine for facts or a code interpreter for calculation. Fourth is the self correction. Finally, it analyzes the output of tool executions and adjusts the plan if the result is suboptimal or if an error occurs. Ultimately, the LLM drives the plan, execute, reflect loop that defines agentic AI. Moving from the agent's brain to its capacity for action, this slide details the two components that facilitate external interaction and goal achievement: tools and the planning loop. The power of tools, the agent's hands. Tools are external modules or APIs like web search, code interpreter, or calendar email APIs that allows the extent to agent to perform actions outside its own knowledge base and interact with the real world. A critical constraint is that agent's ultimate capability is entirely limited by the specific tool it is given access to. The planning loop, the agent strategy. The planning loop is the iterative process that ensures goal completion and self correction. It consists of four critical steps. First is the plan, break the complex code into sequential, tool executable steps. Second is the act, That means execute, select the appropriate tool and execute the current step. Third is observe, that means reflect, analyze the tool's output and update the agent's memory. Fourth is repeat. If the goal is not complete, return it to the planned step with the new information. This loop ensures persistence and self correction until the task is successfully achieved.
This slide, titled Introduction to Agent Design Patterns, serves as a foundational overview for understanding how design patterns apply to intelligent agents in AI and autonomous systems. Agent design patterns are reusable solutions to common problems encountered in the development of agent-based systems. Much like software design patterns in traditional programming, these patterns provide a structured approach to building agents that are efficient, maintainable, and scalable. The slide highlights three key points. Definition: it introduces the concept of agent design patterns, setting the stage for deeper exploration in subsequent slides. Second is the importance in AI and autonomous systems. It emphasizes the relevance of these patterns in modern AI applications where agents must operate independently, make decisions, and interact with other agents or environments. Third is the benefits. The slide outlines the core advantages: scalability, handling growth in complexity or size. Second, the adaptability, responding to dynamic environments, and collaboration, working effectively with other agents. This slide, titled Key Patterns, introduces three foundational agent design patterns that are critical in the development of intelligent and autonomous systems. Each pattern represents a strategic approach to enhancing agent behavior and system performance. First is the reflection. Reflection refers to an agent's ability to introspect, analyzing its own reasoning process and adapting them for improved decision making. This pattern is essential for creating agents that can learn from experience, self-correct, and evolve over time. It supports higher level of autonomy and robustness, especially in dynamic or uncertain environments. Tool use highlights how agents can extend their capabilities by integrating with external tools or resources. This pattern is particularly relevant in real-world applications where agents must interact with APIs, databases, or physical devices to perform complex tasks beyond their native abilities. Third is the multi-agent collaboration that focuses on the cooperative aspect of agent systems. It enables agents to share knowledge, coordinate actions, and work together toward common goals. This pattern is vital in distributed AI systems such as swarm robotics, smart grids, or collaborative virtual assistants. Together, these patterns form a powerful toolkit for designing intelligent agents that are not only capable and adaptive but also collaborative and scalable. In today's evolving AI landscape, the practical deployment of intelligent agents is becoming increasingly impactful. This slide outlines three standout applications: chatbots capable of self reflection, agents that interact with APIs, and tools for seamless automation, and multi agent systems that collaborate in robotics and decision making. These examples demonstrate how agents are moving beyond isolated tasks to become dynamic, context aware systems. The central insight here is the role of design patterns in shaping agent behavior. By applying structured design principles, developers can build agents that are not only smarter but also more adaptable and cooperative. This leads to systems that can handle complex environments, make informed decisions, and work in synergy with other agents or tools. Whether it's enhancing user experience through reflective dialogue or enabling autonomous systems to coordinate effectively, the emphasis on design patterns is key to unlocking the full potential of intelligent agents. As artificial intelligence continues to evolve, the concept of agentic AI frameworks is emerging as a cornerstone in building intelligent systems. These frameworks provide a structural foundation for designing agents that are not only task oriented but also capable of autonomous decision making. The slide introduces the core idea behind agentic AI systems that act with purpose, adapt to changing environments, and collaborate effectively. Frameworks play a critical role by offering speed, modularity, and scalability, which are essential for deploying AI solutions at scale. They enable developers to build complex agents more efficiently, ensuring that each component can be used, reused, upgraded, or integrated seamlessly. Whether it's automating workflows or enhancing user interactions, agentic AI frameworks empower developers to create smarter, more responsive systems. This introduction sets the stage for exploring how these frameworks are revolutionizing the way we think about AI, from isolated models to dynamic, goal driven agents. As the demand for intelligent, task oriented agent grows, understanding the foundational frameworks that power them become essential. This slide presents a concise overview of three leading agentic AI frameworks, each contributing uniquely to the development of smarter, more capable systems. LangChain stands out for its ability to integrate tools, manage memory, and chain reasoning steps, making it ideal for building agents that require contextual awareness and sequential logic. Crew AI that focuses on orchestrating multi agent collaboration, enabling agents to work together efficiently toward shared goals, an approach especially valuable in complex environments. Third is the AutoGen, on the other hand, emphasizes automation within conversational multi agent systems, streamlining interactions and reducing manual intervention. Together, these frameworks represent the cutting edge of agentic design, offering developers powerful tools to build scalable, modular, and intelligent solutions. This overview sets the stage for deeper exploration into how these frameworks can be applied across industries and use cases. In the rapidly advancing world of AI, practical applications are the true measure of frameworks' value. This slide highlights how leading agentic AI frameworks like LangChain, Cream AI, and AutoGen are being used to solve real-world problems. LangChain powers intelligent chatbots and knowledge agents that can reason and respond contextually. Crew AI enables team-based AI collaboration where multiple agents work together to achieve complex goals. AutoGen streamlines automated workflows and supports research tasks, reducing manual effort and enhancing productivity. These examples underscore the versatility and strength of agentic frameworks in diverse domains. The key takeaway is clear. Such frameworks significantly accelerate the development and deployment of intelligent agents. By offering modularity, scalability, and built in capabilities, they empower developers to build sophisticated systems faster and more efficiently. This slide serves as a bridge between theory and practice, showing how agentic design is already transforming industries and workflows. So, I'm going to describe a hands on project focused on building a simple yet powerful research agent. This agent is designed to search the web and summarize information intelligently using a structured workflow known as the plan, act, reflect loop. First, the agent plans by breaking down the user's query into smaller, manageable subtasks and identifying the tools needed like a search engine or code interpreter. Next, it acts by executing the task, typically using web search to gather relevant data. Finally, it reflects by evaluating the results, checking if the subtask is complete, and deciding whether to move forward or refine the plan. This iterative loop enables the agent to handle complex queries with precision and adaptability. Through this project, learners gain practical experience in designing agents that go beyond static prompts, showcasing how thoughtful architecture can lead to dynamic multi step reasoning and real world problem solving. Building on the research agent project, this slide takes a closer look at the reflect phase, an essential part of the agent's plan, act, reflect loop. Reflection is where the agent evaluates the outcome of its actions and decides whether to proceed, retry, or revise its strategy. The pie chart visually breaks down these decisions, showing how often the agent moves forward, refines its plans, or encounters a dead end. This adaptive capability is what makes the agent truly intelligent. The performance metrics are especially compelling: an 80% reduction in research time, 10x more data processing, 98% factual accuracy when grounding responses. These figures highlight the transformative impact of reflection in AI workflows. By continuously learning from outcomes, the agent becomes more efficient and reliable. This deeper understanding of reflection reinforces its role as a critical driver of performance and precision in agentic systems. In Module 4, we will see the practical applications and real world scenarios. Let's begin by addressing a fundamental decision in AI driven workflows: when to use generative AI versus agentic AI systems. This slide presents a clear and practical rule of thumb for tool selection based on the nature of the task. If the goal is creation or transformation, such as drafting an email, summarizing a document, or generating an image, generative AI is the ideal choice. These tasks are typically single step, requiring no external data or interaction. On the other hand, agentic AI shines in scenarios that demand autonomous action and complex problem solving. These systems excel at breakdown goals into subtasks, retrieve live data, and iterating through the plan act reflect loop. Whether it's conducting market research or debugging code across multiple files, Agentic AI offers the flexibility and intelligence needed for dynamic multi step execution. This distinction is crucial for selecting the right AI architecture to match your task's complexity. To make the most of AI capabilities, it's essential to match the right tool to the right task. This slide introduces a decision framework that helps determine whether to use generative AI or an agentic AI system based on task complexity. The framework evaluates two key metrics: required steps and external autonomy. For simple tasks like writing a short poem or summarizing a paragraph, generative AI is ideal. These tasks involve minimal planning, no external tools, and rely solely on the prompt. In contrast, complex tasks such as compiling financial reports or conducting multi step research demand agentic AI. These tasks require dynamic planning, multiple dependent steps, external data access, and memory to track progress. The table clearly outlines how each metric scales with complexity, offering a practical guide for AI tool selection. This structured approach ensures that users can deploy the most effective AI solution for their specific needs, maximizing efficiency and outcomes. When it comes to solving real world problems with AI, choosing the right tool can make all the difference. This slide offers a practical decision guide by mapping common business scenarios to the most suitable AI approach: Gen AI or Agentic AI. For tasks like drafting a summary or creating ad headlines, is the go to solution. These are single step creative tasks that don't require external data or complex planning. On the other hand, tasks like market analysis or booking travel demand a more dynamic approach. Here, agentic AI excels by planning multiple steps, retrieve live data, and interacting with external tools or APIs. The slide concludes with the simple rule: start with Gen AI for straightforward tasks and escalate to agentic AI only when the task involves planning, iteration, or tool integration. This framework empowers teams to deploy AI more effectively, ensuring the right technology is applied to the right challenge. At the heart of every intelligent agent lies a powerful engine, and that engine is the large language model. This slide emphasizes a crucial insight: the LLM is not just a supporting component, it is the core computational brain that drives the autonomy and adaptability of agentic systems. While LLMs are widely known for generating text, their true power in agentic system lies in their ability to reason, plan, and make decisions. In this slide, it outlines three foundational functions that LLMs perform within agents. First, planning and decomposition. The LLM breaks down high level goals into manageable subtasks, enabling structured execution. Second, tool selection. The LLM intelligently determines which external tools like web search or APIs are needed to complete each step. Third is reflection and self correction. The agent evaluates outcomes and adjusts its strategy dynamically, ensuring continuous improvement. These capabilities transform the LLM from a passive responder into an active problem solver, capable of navigating complex workflows. This foundational role of the LLM is what empowers agentic systems to operate with autonomy, adapt to new information, and deliver high impact results across diverse domains from research and automation to decision support and beyond.
This slide explains how a generative language model enables intelligent agents to plan effectively using a technique called chain of thought. Chain of thought prompts the model to articulate its reasoning step by step before taking action, making the agent's internal logic transparent and traceable. This structured reasoning is vital for complex tasks as it allows the agent to store and reflect on its thought process. This slide illustrates a typical flow. The agent begins with a goal, that is, booking a flight, select a tool, an API performs an action, observe the result, and reflects to define its next steps. This modular approach, where the LLM handles planning and external tools execute actions, ensures clarity and separation of concerns. Overall, the slide emphasizes how chain of thought transforms LLMs from passive responders into proactive planners, capable of reasoning, acting, and learning iteratively. This is foundational for building autonomous, goal driven AI agents. The synthesis phase, as depicted in this slide, showcases the generative model's strength in high level abstraction. Once the agent completes its planning and execution loop, the Gen AI component takes over to perform a final value added task, transforming fragmented memory into coherent output. This includes summarizing retrieved facts, organizing successful and failed actions, and presenting them in human readable formats like reports or tables. The slide emphasizes how Gen AI's reasoning capabilities enable it to distill complexity into clarity. Importantly, it highlights the synergy between agentic tools and generative intelligence. Tools ensure factual accuracy through real time access, while Gen AI enables problem decomposition, error correction, and synthesis. This layered architecture allows the system to go beyond raw data dumps, delivered refined insights. By blending planning, execution, and synthesis, the agent becomes far more capable than a standalone LLM, offering a robust framework for intelligent decision making and communication. In today's fast paced financial landscape, autonomous AI agents are redefining how institutions manage trading and risk. This slide presents a compelling overview of how agents bring speed, precision, and scalability to decision making. In algorithmic trading, agents leverage real time data from market APIs and news feeds, plan complex strategies, and reflect on market volatility to optimize execution. Their ability to adapt dynamically makes them invaluable in minimizing slippage and maximizing returns. On the compliance front, agents collaborate across domains, tracking user behaviors, geographic anomalies, and regulatory shifts to detect fraud and ensure adherence to evolving standards. The use of memory allows these agents to maintain historical transaction patterns and risk profiles, enabling continuous evaluation. The key takeaway is clear: AI agents transform financial operations from reactive analysis to proactive autonomous action. This shift not only enhances efficiency but also empowers institutions to stay ahead in an increasingly data driven and regulated environment. In the evolving landscape of healthcare and life sciences, AI agents are emerging as powerful catalysts for precision medicine and accelerated research. This slide highlights how agents enhance both clinical decision making and drug discovery by leveraging their ability to process vast complex datasets. For personalized treatment planning, agents integrate patient history, genomic data, and the latest medical literature to generate tailored therapeutic recommendations. Their use of planning, memory, and tool access ensures decisions are both data driven and context aware. In drug discovery, agents simulate molecular interactions, reflect on outcomes, and iteratively refine compounds, dramatically reducing lab time and cost. By automating these high dimensional tasks, agents not only improve efficiency but also unlock new possibilities in personalized care and biomedical innovation. The key takeaway is clear: AI agents are not just augmenting healthcare, they are transforming it, enabling scalable, intelligent systems that support clinicians and researchers in making faster, more informed decisions. As software systems grow in complexity, AI agents are stepping in as intelligent collaborators across the development lifecycle. This slide illustrates how development operations agents are evolving from simple code generators to autonomous maintainers of software infrastructure. In debugging and refactoring, agents analyze error reports, plan multi-step fixes, run code in live environments, and iteratively test their solutions, dramatically reducing developers' workload and turnaround time. In system monitoring, agents operate with goal-oriented precision, maintaining high uptime by predicting failures and taking corrective actions via cloud APIs. Their ability to autoscale resources or restart services ensure resilience in large-scale deployments. The integration of planning, tool use, and reflection enables these agents to handle tasks that were traditionally manual and time consuming. The key takeaway is clear: development agents are not just supporting developers, they are transforming software maintenance into a proactive, intelligent process, paving the way for more reliable, scalable, and efficient systems. As artificial intelligence continues to evolve, the nature of human AI interaction is undergoing a profound transformation. This slide introduces the concept of human AI symbiosis, marking a shift from AI as a passive tool to an active collaborator in decision making and problem solving. The collaboration spectrum, ranging from human led machine assisted models to machine led human assisted systems, captures the diverse ways in which humans and AI can work together. Importantly, the slide emphasizes the complementary strengths of each. Humans bring intuition, creativity, ethical judgment, and adaptability, while AI contributes unmatched capabilities in data processing, consistency, and scale. This framework encourages organizations to design workflows that harness the best of both worlds, tailoring collaboration models to the context and complexity of the task. Ultimately, the slide sets the stage for a future where human insight and machine intelligence coalesce to drive innovation, efficiency, and responsible decision making across industries. As AI continues to evolve, the convergence of advanced technologies is reshaping how humans and machines collaborates across industries. This slide outlines the foundational technological drivers: agentic AI, large language models, multimodal AI, and learning paradigms like reinforcement and transforming learning that are enabling more intelligent, adaptive, and explainable systems. These innovations are not just theoretical, they are actively powering transformative applications. In healthcare, AI augments diagnostics and treatment planning, improving outcomes and efficiency. In finance, agents detect fraud and simulate market behavior with precision. Creative industries benefit from AI-driven co-design, unlocking new forms of artistic expression. Meanwhile, autonomous systems such as drones and cooperative robotics are becoming more capable and context aware. The inclusion of interpretability and explainability ensures that these systems remain transparent and trustworthy. Overall, the slide presents a compelling vision of how cutting edge AI technologies are driving real world impact through collaborative intelligent applications. As AI becomes deeply embedded in the workplace, organizations must rethink how humans and machines collaborate. This slide outlines the emerging hybrid workforce model, emphasizing the need for human in the loop protocols, AI literacy, and adaptive problem solving. These skills are essential for navigating a future where AI augments, not replaces, human capabilities. The strategic principles presented offer a roadmap for responsible integration, designing systems that complement human cognition, fostering continuous feedback between humans and AI, and ensuring ethical, explainable AI practices. Importantly, the slide reinforces that AI should serve as a tool for augmentation, enhancing human decision making rather than automating it away. The key takeaway is clear: the future of work will be shaped by symbiotic intelligence, where trust, adaptability, and lifelong learning are central. Organizations that embrace these principles will be better positioned to unlock the full potential of AI while empowering their workforce to thrive in a rapidly evolving landscape. So, in Module 5, that we'll be covering some advanced topics and conclusions like ethics and governance in AI, deployment and production, best practices for taking AI projects, and final project that we will discuss a multi-agent system and further course conclusion and next steps. As AI systems become more powerful and autonomous, ethical governance is no longer optional. It's essential. This slide sets the stage by distinguishing between Gen AI, which creates content, and Agent AI, which makes decisions and takes actions independently. Both bring immense potential, but also serious risks. Gen AI can propagate misinformation, bias, and copyright violations, while Agent AI raises concerns around control, accountability, and safety. The slide emphasizes the core reasons ethics matter: prevent harm, ensure fairness, build trust, and align AI behavior with human values. These principles are foundational for responsible AI development and deployments. As organizations increasingly rely on AI for critical tasks, embedding ethical safeguards become vital to maintain public confidence and avoid unintended consequences. Ultimately, this slide calls for a proactive approach to AI governance, ensuring that innovation is guided by integrity, transparency, and a deep respect for social impact. As AI systems become increasingly embedded in decision making processes, understanding and addressing their ethical implications is critical. This slide highlights four core risks that must be actively managed to ensure responsible AI deployment. Bias and discrimination remain pressing concerns, as AI can unintentionally reinforce societal inequalities if trained on skewed data. Transparency and explainability are essential for building trust. Users must be able to understand how and why decisions are made. Privacy and consent are foundational to ethical data use, requiring clear boundaries around how personal information is collected and applied. Finally, autonomy and control, especially in Agent AI, raise important questions about accountability when machines act independently. These considerations are not just technical challenges, they are societal imperatives. By embedding these principles into AI design and governance, organizations can foster systems that are fair, trustworthy, and aligned with human values, paving the way for ethical innovation. As AI technologies advance rapidly, establishing a robust governance framework is essential to ensure safe and ethical deployment. The slide outlines a multi-layered approach to building guardrails around AI systems. At the regulatory level, initiatives like the EU AI Act and India's DPDB will reflect growing global momentum towards formal oversight. Within organizations, corporate governance plays a critical role through ethic boards, audits, and risk assessments that guide responsible innovation. On the technical front, safeguards such as model interpretability, red teaming, and human in the loop systems help mitigate risks and maintain accountability. These mechanism ensures that AI system remains transparent, secure, and aligned with human values. The slide also points to a future outlook where policy and technology co-evolve, adapting governance as AI capabilities grow. Together, these elements form a comprehensive strategy for deploying AI responsibly, balancing innovation, trust, safety, and societal impact.
Transitioning an AI model from the lab to a live environment is a critical phase that demands both strategic planning and technical rigor. This slide effectively outlines the foundational steps required to bridge the gap between development and deployment. The model readiness checklist ensures that the AI system is not only high performing on a real world data but also fair, explainable, and free from unintended bias. Key factors for building trust and ensuring compliance. Equally important is environment preparation, which emphasizes the need for scalable infrastructure, robust CI/CD pipelines tailored for machine learning, and meticulous version control for both models and datasets. These elements are essential for maintaining reproducibility, traceability, and operational efficiency. Together, these practices lay the groundwork for reliable, ethical, and scalable AI deployment. This slide serves as a concise yet comprehensive guide for practitioners aiming to operationalize AI responsibly and effectively in real world settings. Successfully deploying an AI model into production requires more than just technical accuracy. It demands a holistic approach to readiness and infrastructure. This slide outlines the essential steps to bridge the gap between development and deployment. The model readiness checklist ensures that the model performs reliably on a real world data, has undergone bias and fairness evaluations, and offers transparency through explainability and interpretability. These environments are critical for building trust and ensuring ethical compliance. On the infrastructure side, environment preparation focuses on scalability, whether cloud basis based or on premises, and emphasizes the importance of CI/CD pipelines tailored for machine learning workflows. Version controls for both models and data is highlighted as a best practice for maintaining consistency and traceability. Together, these components form a robust foundation for operationalizing AI solutions
that are not only technically sound but also responsible, scalable, and maintainable in dynamic production environments.
As AI systems move from experimentation to enterprise deployment, governance and risk management become critical pillars of responsible innovation. This slide emphasizes the importance of establishing robust governance frameworks to ensure transparency, accountability, and compliance. Key practices include maintained detailed model documentation and audit trails, implementing role based access control, and aligning with global regulations such as GDPR and India's DPTP bill. On the risk mitigation front, the slide highlights the need for human in the loop protocols for high stake decisions, fail safes, and fallback mechanisms to handle unexpected behavior, and ethical review process to evaluate potential societal impact. These measures not only safeguard against technical failures but also build trust with users and stakeholders. In an era where AI decisions can have real world consequences, this slide serves as a blueprint for deploying AI systems that are not only effective but also ethically sound and legally compliant. As AI systems evolve, the ability to design collaborative, autonomous agents become a cornerstone of advanced problem solving. This final project challenges learners to build a multi-agent system capable of tackling complex real-world scenarios through intelligent coordination. The first slide sets the foundation by outlining the project's objective to implement agents with distinct roles that interact via shared memory or communication protocols. The integration of planning, tool use, and reflection ensures that the agents not only act but also adapt and learn, hallmarks of agentic intelligence. In the second slide, it deep dives into design considerations, emphasizing the importance of architectural clarity. Role specialization allows agents to focus on specific tasks, while robust communication strategies such as message passing or shared memory enable seamless collaboration. Error handlings and fallback mechanisms are critical for resilience. The technical stack includes LLMs, APIs, and essential tools for monitoring and debugging, ensuring the system is both functional and maintainable. Finally, the third slide outlines evaluation and presentation criteria. Success hinges on the system's robustness, the clarity of agent interactions, and the relevance of the problems addressed. Learners are encouraged to present their work through live demos or walkthroughs, supported by architecture diagrams and reflections on challenges faced. This project not only reinforces technical skills but also cultivates strategic thinking, making it a fitting capstone for course focused on agentic AI. As artificial intelligence continues to evolve, understanding the distinction between Gen AI and agentic AI becomes essential for anyone working in the field. The first slide clearly outlines the core differences. While generic AI is reactive and excels at generating content based on prompts, agentic AI is proactive, capable of planning, using tools, storing memory, and reflecting on outcomes. This shift from assistant to autonomous collaborator marks a significant leap in AI capabilities, enabling systems that can reason, act, and adapt independently. The second slide explores the broader implications of agentic AI. It highlights how this paradigm shift is transforming industries from healthcare and finance to software and education by enabling autonomous workflows and multi agent collaboration. However, it also introduces new challenges in ethics, governance, and human AI interaction, urging developers and organizations to rethink how they design, deploy, and regulate intelligent systems. The final slide offers practical next steps for continued learning. It encourages learners to explore advanced topics like multi agent systems and reinforcement learning, build real world projects with iterative experimentation, and engage with the global AI community through conferences and research forums. The closing thought is both visionary and actionable. The future of AI lies not just in smarter models but in intelligent agents that function as teammates, capable of reasoning, collaborating, and evolving alongside humans. Together, the slide provides a powerful conclusion to the course, inspiring learners to embrace the future of agentic AI
with curiosity, responsibility, and innovation. Thank you.